one might ask, how do we determine the moment of inertia or rotational inertia of an object? In the case of inertia or mass for linear motion, all what we had to do is use a scale. Okay, of course, there are other methods for measuring the mass, but the most commonly used one is a scale. For rotational inertia, it's not going to be as easy. Part of the reason for the difficulty is the fact that the moment of inertia is going to depend on the axis about which the object is going to rotate. Or, like it was mentioned earlier, an object can have many moments of inertia depending on the many axes of rotations we can choose for that object to rotate about. The simplest case is for a mass m going around in a circle of radius r. In that case, its rotational inertia or moment of inertia is given by that expression. I is equal to mr squared. We use I for inertia, the symbol for moment of inertia or rotational inertia. And it is equal to the mass of the object times the radius of the circle about which that mass is rotated. Now, what if I have a more intricate object, an object, let's say, that has another mass m2 that's attached to it, and that's rotating with a radius r2 instead of r. In that case, the overall moment of inertia is going to be the sum of both moments of inertia. I overall is going to be I1 for the original mass plus I2. I1 for the original mass is mr squared. For the second mass, it's m2 r2 squared. And then if I have a third mass, I have to add it and so on. So this is where we express that in general. The moment of inertia is the sum, that symbol is for sum, of the various masses times the corresponding radius for each of the masses squared. That's the way we get the moment of inertia. And we'll see that it's not as simple as that, but we'll see implications of that shortly. Now, one more thing before we talk more about that, the axis of rotation. How do we determine that? Usually, the axis of rotation is determined through a physical constraint, something that we impose on the object. For example, when we had the stick and the gentleman from Louisiana trying to balance it, so that object, the physical constraint is where the stick was touching the finger. So that stick can rotate about the finger. So that's, in that case, my axis of rotation. When his kids were trying to spin the sticks with the juice boxes, they were trying to spin them about their center. That's another physical constraint. Naturally, if you toss an object, if you kick an object, it's going to tend to spin about its center of mass. We'll talk about center of mass shortly, but it's going to try to spin about its center of mass, unless there is a physical constraint. Now, the center of mass of an object like this is in the middle, for example. In this case, the center of mass is probably in the middle here, but we are getting it to spin about something away from the center of mass. Let's look a little bit in the case of the stick being balanced by the finger. Now, if you recall the equation that we have used, we said it is mr squared, or in more intricate cases, the sum of mi's ri squared. This illustrates that very well. When you consider the stick, there is this small mass here, this small part of the stick, let's call it m1. The radius of that small mass, the radius of rotation, is r1. Then there is the small mass M2. The radius for that small mass is R2. Then we have M3, R3, and M4, R4, and so on. So the overall moment of inertia is going to be tricky because that stick can be considered as a multitude of small masses. Each one of them has a different radius relative to the axis of rotation. Okay, we'll see how do we handle that usually in a little bit.